Good day, everyone, and thank you for joining us. My name is Steve Matza. I'm the Chief Scientist for Zymeflow. Many of you are already familiar with Zymeflow, as we have decontaminated various process units across many refineries and petrochemical plants in the Middle East. But today we're going to focus on a specific unit, and that would be reactors. In today's webinar, we will take a look at the state of cleaning reactors that have fixed bed catalysts. We will then share with you a leading edge technology that can enhance the standard practice with benefits to the timeline, cost, safety, and predictability. The reactors we'll be considering are known as hydroprocessing units, and these include hydrotreaters, hydrocrackers, isomerizers, and reformers, among others. Reactors with fixed bed catalysts normally require a change-out when they are brought down due to a performance problem. Catalysts can lose activity due to either poisoning or physical blockage of the active sites by heavy hydrocarbon deposits. As you all know, there are several alternatives for cleaning reactors, but of these, the best practice is likely to be the hot hydrogen sweep nitrogen purge. This widely used practice involves the sequenced application of dry gases through a reactor circuit after the feed has been cut out. The hot hydrogen serves to soften coke so that H2S, LEL, and benzene are liberated and can be swept out by the hydrogen stream. The nitrogen then serves to purge out any remnant LELs along with the hydrogen and cool the reactor for eventual catalyst offloading. This schematic shows a little more detail of the hydrogen sweep nitrogen purge. After the feed has been cut out of the unit, hydrogen is passed through a heater and into the reactor section, where it wafts through the catalyst, pushing H2S, LEL, and benzene toward a colder region of the unit known as a separator vessel. In the separator, some of the contaminants condense while others do not. Those that do not condense are routed to the flare or flare gas recovery unit. The condensed materials can be drained from the separator and sent normally to a slop tank or some other waste destination. When the LELs have reached a sufficiently low level during the hydrogen sweep, the hydrogen is blocked in, the nitrogen purge begins, and the nitrogen pushes out residual LELs, hydrogen, which is itself an LEL, and then also serves to cool the unit for offloading. You'll notice the nitrogen purge has very little in the way of condensed materials because most of that was removed during the previous hydrogen sweep step. There are many benefits to using the hydrogen sweep nitrogen purge. The use of dry gases means that very little effluent is produced, and that which is produced can be reprocessed in-house. Hydrogen is a process utility and readily available. And this reactor cleaning method is a high temperature method, which means it can start relatively soon after the reactor has been brought off of high process operating temperatures. This technique is not without its drawbacks, though. It is unpredictable. There are occasions where persistent stubborn LELs require days of purging. This extra purging time can lead to excessive utility costs. And for many clients, nitrogen is much more expensive than hydrogen. The excessive purge times can also complicate scheduling time on the flare. Some clients also experience clumping of the catalyst during offloading due to these hydrocarbon deposits, and may also encounter entrapped LEL in the deposits during the offloading process, which can not only interrupt the timeline, but pose an extreme hazard to personnel safety. We sought to solve some of the problems of the current practice, but to do this, we identified several root causes. Among these were the deposition of heavy hydrocarbon deposits on the catalyst and an unpredictable timeline for the removal of LEL. In order to solve this problem, we developed a solvent chemistry that could serve as an adjunct to the standard practice by injecting the chemistry directly into the hydrogen sweep. This solvent chemistry is designed to dissolve the asphaltene binders that glue coke together. The chemistry is also an excellent scrubber to absorb the heavier LELs that are often the most difficult to remove. This scrubbing capability provides a second mechanism for LEL removal that can complement the purging action of the hydrogen. The chemistry is known as CatZyme. It is a high-boiling, solvent-based chemistry that is compatible with catalysts in every respect. It contains no surfactant, no nitrogen, no sulfur, none of the known or suspected catalyst poisons, which are usually metals or cations. Referring back to our process description, you can see that the impact of including CatZyme is very little on the process itself. After the hydrogen sweep is established, as before, the chemistry is injected at a point either immediately preceding or following the heater, using an air-actuated drum pump. As the chemistry encounters the hydrogen, it's vaporized and transported through the reactor. After the chemistry has performed its function, it then collects in the separator vessel. And being a high boiling formulation, it is completely condensed in the separator. This gives an avenue to recover and isolate the chemistry from the reactor circuit. It can simply be drained from the separator and routed to slop to be reprocessed with the other waste. The CatZyme timeline is very interesting when compared to the traditional hydrogen sweep nitrogen purge. This timeline shows all the stages of a reactor cleaning. The chemistry plays very little part in either the de-inventory or the viscosity wash stages. And that's because it's only added after these stages. The chemistry can be seen to have a significant impact on the hydrogen sweep timeline due to the solvency of the chemistry for deposits and the scrubbing of LELs. There can even be an impact to the nitrogen purging phase because the sweep with hydrogen was so effective at removing LEL. Now the nitrogen only has to push out hydrogen, which is much lighter and easier to move than heavier LELs. The solvent chemistry can reduce the incidence of clumping during the offloading stage and minimize the risk of encountering embedded and trapped LELs during the offloading process, which could cause additional interruption and personnel safety issues. Overall, you can expect about a 40% savings in the timeline using the CatZyme technique relative to traditional hydrogen sweep nitrogen purge. Of course, the exact time will depend on the catalyst lifetime, as well as the quality and consistency of the feed materials to the reactor. The CATZyme process also includes a measurement step to both recognize and assure that the hydrogen sweep has removed LELs. The hydrogen stream is sampled using a pressurized device called a sample bomb. The bomb contents are analyzed by headspace gas chromatography, which is a technique that can monitor the removal of H2S, LEL, benzene, and any hydrocarbon that contains 4 or more carbons. This is a widely used technique available in most refinery labs that's often used on a frequent basis to monitor the hydrogen utility. After the LELs have been removed to a sufficiently low level, the hydrogen's blocked in, the nitrogen purge starts. The only significant LEL remaining is essentially hydrogen. To monitor the nitrogen stream further, all that's required is a simple 4-gas meter operating in the LEL mode. Once the nitrogen purge is complete, the reactor cleaning is essentially finished and offloading can begin. So in summary, let's review. Why would you use CATZyme? The CATZyme process provides an insurance policy for a reproducible, predictable reactor cleaning timeline. Relative to the historical hydrogen sweep nitrogen purge, the CATZyme process can save timeline, it can reduce utility costs, and reduce purging times translate to less time on the flare. The solvency of the chemistry allows you to avoid clumping problems during the offloading, as well as minimizing the chance of encountering entrapped LELs, which could interrupt the offloading, causing significant delays, and more importantly, providing a hazard to your personnel's safety. At this point, I would like to thank you for your attention, and if you have any questions, our panel of experts will be more than happy to answer them in the ensuing section.